Hi everyone, welcome to our sort of lesson on 8.2. And I say that because we're not really going to pay a whole lot of attention to what the textbook sets out in section 8.2. Section 8.2 in the textbook is about transformations of logarithmic functions. And transformations of logarithmic functions are even less useful than transformations of exponential functions. And in that sense, where we barely spent any time looking at transformations of exponential functions, we're going to spend even less amount of time looking at transformations of logarithmic functions. The only thing that we're really going to care about, I'm just going to draw a quick sketch here, is in exponential functions, we cared about looking at exponential functions that had a vertical translation, because that vertical translation that we saw would give us a change in our horizontal asymptote. Well, applying the idea that logarithmic functions are the inverses of our exponential functions, a vertical translation in an exponential function corresponds into a horizontal translation of a logarithmic function. Now, in terms of actual applications, we're not going to see this in most of the questions that we model, so we're not really going to pay too much attention to it, but it is good for us to understand that that's what's going to happen. What we're going to really focus on when we get into section 8.2 is how we use logarithms to solve word problems. And so we're going to go back and take another look at one of the questions that we've already taken a look at before. And so we're going to solve this question about the Iceman using logarithms this time instead of graphing. We will need to use a graphing calculator or a calculator that has a log base button, as we are going to need something besides a log base 10 to solve this problem. As we go further into the chapter, we'll understand how to do that with any question. So as we work our way through this question, it should be familiar to us. We're looking at the amount of carbon-14 present in a mummified human body. We find that 47.3% of the carbon-14 present had decayed in the year 2001. So we're going to set up our variables. I'm going to use y to be the amount of C14 present, and I'm going to do that in a percentage. You can, of course, do that as a decimal if you want to as well. And then I'm going to set up my x to be time in years from 2001. You can, of course, set this up to be the time in years from the time that the Iceman died. We're going to get the same answer. We just have to think a little bit more about if our x's are going to be positive or negative. So if I have 47.3% of the carbon-14 has decayed in 2001, that tells me that I have 52.7% of that carbon-14 left in 2001. And I'm going to keep that in mind when I go to set up my equation. So as I set up my equation, I'm going to end up with y equals 52.7. We have a base of a half, because it's a half-life equation, and it takes 5,730 years to decay by a half. Okay, so I am looking to find when I have 100% of the C14 when I go to solve this with a logarithm. I have to sort of think about what we've talked about with logs so far. I'm going to make a switch of representation. So if I have an equation that's in the form y equals c to the x, I know that I can then turn that into log base c of y equals x, right? What is the power on a base c number that gives me y? Well, it's x based on that representation. So I need to take care of the coefficient on the right side of the equation before I'm able to switch my terms. So I'm going to, or sorry, I should say switch my expression from exponential to logarithmic. So as I go through and I divide by the 52.7, I'm going to keep an exact number here, so I'll get 1,000 over 527 equals 1/2 to the x over 5,730. And I'm going to use the same patterns that we were seeing in the first part of this chapter to rewrite this exponential equation into an equivalent relationship between these values, but write it as a logarithm. So we know the base stays the same. So that's going to get me a log base 1/2 of 1,000 over 527, and that's going to be equal to x over 5730. Now, to get x by itself, I'm going to have to multiply by 5,730. Now I'm just going to switch sides here. So I'll move the x over to the left-hand side, and I'm still multiplying through by 5730 times the log base 1/2 of 1,000 over 527. So I'm going to have to go to my calculator now and use my log base button. So if I just do a quick switch here, we'll bring up the calculator. Under math, now your menu will look a little bit different, but we find our log base. We want to do a log base of 1/2 of 1,000. Just delete that. 1,000 divided by 527. And that gives me a negative value, which I then multiply by 5,730 to give me negative 5295. So that gives me negative 5295. We know that we then, to answer the question, if I jump back up there again, I'm looking for the approximate century in which he died. So I take the year in which we had the sample when we had 52.7% of the carbon-14 left. We go back by 5,295 years, and that gives us approximately the year negative 3,300. So the century we're looking at is 33 BCE. Okay. So if you look at what we just did, there isn't really a whole lot of differences from what we had done previously. The main difference is that, well, in terms of the setup, everything's exactly the same. The main difference is at this step here, we would have graphed it and we would have come up with an answer. But now we can go through and we can do this rest of this procedure and we can solve that algebraically. As we move forward in this section and throughout the rest of the chapter, we're going to see how to use logarithms to work our way through and solve these questions. One other thing that I should note, if you look at where we did our switch, so if you look at this section here between those two lines, another way that you could think about going from the line 1,000 over 527 equals 1/2 to the x over 5730 down to the logarithmic equation. We did the definition that we saw of what a logarithm is, but understanding that logs are inverses of exponential functions or an exponential operation. If I took the log base 1/2 of both sides of the equation, I get the exact same thing on the left side, but I would have log base 1/2 of 1/2 to the x over 5730. Those are inverse operations, which would just leave me with the exponent. So I sort of have two ways to think about going from an exponential equation into a logarithmic equation and solving from there. But as we move through the next little bit, we will see this procedure done again and again, and this is the main reason we have looked at logarithms, because logarithms allow us to get a variable out of an exponent, and we haven't been able to do that up to this point. So there's nothing else that we need to do for today. Just make sure you take a good look at this example and be ready for our next class where we'll get some practice in.